Okay, so we are back to the carbohydrates. So we talked about in the previous session about the types of the carbohydrates, which is our mainly individual sugars, monosaccharides, and how they undergo oxidation and reduction, and what are the names that they get when they do those kind of reactions. Now these monosaccharides, you can see there are lots of hydroxyl groups, and also it has a carbonyl group. Now we have learned in previous chapters that hydroxyl groups and the carbonyl groups can combine to form hemiacetals and acetals. So these monosaccharides also undergo these types of reactions. What we are seeing here is a Fischer projection of a D-glucose. Okay. So this is your D-glucose, and if you number it, we start with the carbonyl, carbon giving the number 1 priority. 1, 2, 3, 4, 5, 6. Okay. Now this straight chain, they undergo cyclization, and during this cyclization they can form hemiacetals. Do you remember what is a hemiacetal? We learn about hemiacetals. So hemiacetals are basically, let me draw those. Okay. So basically hemiacetals are when you have a carbon, you can have a carbon, and then you can have oxygen. And hemiacetals are when you have a hydrogen as alcohol on one side, and then you can have ether, alkoxy group as one. So those are hemiacetals. What are acetals? So the acetals, if you remember, they are, you have a carbon, you can have OR group. So those are acetals. And this is a hemiacetal where you have a carbon, OR group, and OH group. So they are hemiacetals. Okay. So these groups also undergo this acetal and hemiacetal formation. So this is our Fischer projection of the D-glucose. Okay. So you can bend it, and you can bend the molecule, and according to the numbers that you can see, 1, 2, 3, 4, 5, 6. So the number 1 is your carbonyl carbon, and we are going to make a 6-membered ring. So the 6-membered ring is going to form between number 1 carbon and the OH group on the number 5 carbon. So I'm going to go back to my PowerPoint slides. Okay, here. See number 1 carbon. You see the number 5 over here. Number 5 have a oxygen on it. So the 5-membered and the 6-membered rings are the most stable. So we're going to make a 6-membered ring. Okay. Meaning there are, we need to have 6 atoms. So 1, 2, 3, 4, 5. And then the 6th atom is the oxygen on the number 5 carbon. Okay. So when you bend this molecule, carbonyl carbon is here. And then number 2, number 3, number 4, number 5. Number 5 oxygen, you draw it vertically like this. And then the group on the number 5, you're gonna draw it facing up. Okay. Now when you are drawing these cyclic molecules, we call them as Haworth projection. Going from Fischer projection to the Haworth projection, we need to pay attention to our alcohol group. So there is a way that we can represent whether the alcohol groups on the Fischer projection was on the left side or the right side. So whichever hydroxyl groups on the right side, the blue hydroxyl groups, the right side OH will end up being facing downwards, like this. You see here? Groups on the right in a Fisher projection are down in a Haworth projection. Okay, groups on the left, this red OH, Fisher projection are up in a Haworth projection. So we need to remember that. Groups on the left will be facing up. So number 1 carbon is your carbonyl group. Number 2 is right, hydroxyl group right. So the OH is facing down. Number 3 to the left facing up. 4 to the right facing down. And on the 5th carbon, you can see there is a OH group. Now this is the oxygen. We are going to react with the carbonyl group. So we need to write this in vertical fashion, like this, because they need to come closer to each other. And then the remaining group 6 CH2OH will end up facing up. So that is the way that we draw Haworth projection from the Fisher projection. Okay. Now once you get this to this form where they both are in the close vicinity, so the lone pair of the oxygen attack the carbon, break the carbon-oxygen pi bond, making a new bond between this carbon and oxygen. And there will be this hydrogen, and a water molecule will come and take this hydrogen. You know all that process. So now we have made a ring with 6 atoms on it. Okay. This is called Haworth projection. Now we are going to form an alcohol on this carbon. So this alcohol, the newly formed OH group, could be either facing down or could be either facing up. Okay, so the new carbon, that the bond that is being made with this oxygen, where we have the hemiacetal. Remember, the hemiacetal is the carbon with a OH group and carbon with a OR group. So this is a hemiacetal carbon. That carbon is called anomeric carbon, which is a new asymmetric center, because this number 1 carbon has a hydroxyl group, oxygen and another carbon group, and this carbon has this group, a different group, and also a hydrogen. When the OH group is facing down in the anomeric carbon, we call it as a alpha D glucose, facing down. When the OH group at the anomeric carbon facing up, we call it as a beta D glucose. And one of my students in a previous class told me how she remembered OH facing down. Remember, the anomeric carbon OH facing down is alpha. Alpha, how does it look like? Alpha look like a fish. Where does the fish grow? Do they fly in the sky? No, they are on the ground in the rivers, right? So, and the ponds. So the fish is down. So alpha is OH group facing down. Okay, and then the beta is just look like a bird, beta bird. Birds go in the sky, so it's facing up. And this alpha beta designation is given for the anomeric carbon hydroxyl group. Okay, so we can see that the D-glucose exists in 3 different forms. What are the 3 different forms? The Fisher projection and also in the 2 types of Haworth projections. Okay. Alpha D-glucose and beta D-glucose. Beta meaning its OH group is facing up, alpha OH group facing down, like that. Alpha D-glucose and beta D-glucose are anomers. Now alpha and the beta, they differ only at the anomeric carbon, right? Because the rest are the same. So this OH down, this OH up, this is down, OH, this group is up. So we call them as anomers. They are alpha and beta D-glucose they are anomers. 2 anomers of the D-glucose. This is the alpha facing down, facing up. And what are these 2? They are hemiacetals. And another one. So now this one, these Haworth formula or the projection, we have how many atoms? 6 atoms. It's a 6-membered ring. 1, 2, 3, 4, 5, 6. And some monosaccharides form cyclic hemiacetals with 5-membered rings, like the D-ribose over here with 5 carbons. Okay, 1, 2, 3, 4, 5. So the carbon 1 and the hydroxyl group oxygen on carbon 4 combine to form a hemiacetal or a Haworth projection. So we can bend the molecule. Carbonyl group is over here. 2 carbon 2 OH to the right goes down. OH to the right goes down. And then the fourth one, we need this oxygen to form the bond, and then the other group as a convention stays up. Okay. So form the alcohol group over here, and if it is facing down, alpha D ribose, facing up, beta D ribose, anomeric carbon. So these are 2 anomers of D ribose, and this is a 5-membered ring. And then we give a name for these 6 and 5-membered rings. Normally, so this is a 6-membered ring with oxygen with 5 carbons. This is a pyran molecule. Furan is 1 oxygen and 4 carbons with a 5-membered ring. Pyran and furan, they are known compounds. So we adopt the name, the same name for these glucose. If it is a 6-membered ring similar to pyran, that would end as a pyranose because this is a sugar. So this is alpha D glucose. It will be named as alpha D glucopyranose. This is alpha D ribose, that would be named as alpha D ribofuranose. Furanose because it is 5-membered ring. So 6-membered ring sugars are called pyranoses. 5-membered ring sugars are called furanoses. So this is this one, alpha D fructofuranose, alpha D fructofuranose, and this is beta D fructofuranose. This is anomeric carbon, alpha facing down, beta facing up, and this is a 6-membered ring can be formed from fructose. This is alpha D fructopyranose because it is a 6-membered ring. This is beta D fructopyranose, another 6-membered ring. And this glucose Haworth formula, which has a 6-membered ring, we can also represent it as a chair conformer. So this is our Haworth projection, and there are 6 atoms. Excuse me. This can represent as a Fisher projection, not the Fisher, sorry, chair conformer. Okay, chair conformer. So this is your oxygen, and this is number 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and then the 6th carbon. Okay, this is facing down, you facing down. OH group is axial. 2, the second one again. So this is facing down, so you have to draw in your chair conformer also facing down. When it faces down, that would be axial because there are 2 bonds here. One is axial, this is equatorial. So this is going to be equatorial. And on the 3rd carbon, OH facing up, so here facing up is equatorial. One is facing up. 4th carbon facing down, that also represent as it is equatorial facing down. And then the 5th one, over here the 2 bonds are going to be axial, one would be facing down, equatorial one is the one that facing up. So when you draw your glucose, you can see most of these alcohols and these groups are all equatorial. Only the alpha D glucose hydroxyl group at the anomeric carbon is the axial one. Okay, so that was the alpha D glucose, and then similarly we can draw the beta D glucose same way, and then here the OH group is going to be equatorial. All of these are equatorial. Okay, so remember, when the in a chair conformer, if all the bonds are equatorial, they have added stability because they minimize the 1,3 diaxial interactions. So the steric hindrance will be minimal about the groups. Okay, when they are axial, they can have 1,3 diaxial interactions. Excuse me. So that is why the glucose is the most stable aldohexose, and also that we will see the glucose as the most abundant monosaccharide. It's more stable, having all the OH groups equatorial. So this is alpha D glucose, only group is OH group being axial, 36%. And then here the equatorial, all of these groups, so they are going to be 64% beta D glucose. And this is the open chain. Beta D glucose more stable than the alpha D glucose because all the groups are equatorial here, all the groups are equatorial except OH group here, that is the axial one. Now comparing glucose to another sugar, galactose. If you remember the galactose is a C4 epimer of glucose, meaning in the carbon 4 this is facing down OH group, and galactose it would be facing up. So here you have hydroxyl group facing up, and also here you have OH at carbon 1 axial alpha group. So one group is facing up, that generate 1,3 diaxial interactions and making it less stable compared to glucose. Okay. So the OH at C4 is axial. And this is glucose. In the glucose also, excuse me, it differs in configuration from glucose at C3 and C4. So its OH groups at C3 and C4 are axial. So you see here another sugar, glucose. So there are two hydroxyl groups that they are axial. Again, that would create steric hindrance, 1,3 diaxial interactions, making they are unstable compared to glucose. So comparing to other sugars, that is why we see glucose as the most abundant sugar. Okay. And this is the L-glucose. Even the L-glucose, we will have two hydroxyl groups facing axial orientation. Okay. Formation of glycosides. So glycosides, now in the previous part we learned that when the cyclic form is formed, we create hemiacetals. So the formation of a glycoside creates a formation of an acetal. Remember, acetal is the carbon with two alkoxy groups, OR groups. Now this is beta D glucose. Remember, the beta is the anomeric carbon hydroxyl facing up. Or we can call it as beta D glucopyranose because it's a 6-membered ring, which is a hemiacetal. Now you add ethanol to this one. When you add ethanol, this hydrogen, this OH group will be replaced by this ethoxy group. You see here? Now we call that as a glycosidic bond. Glycosidic bond is this hydroxyl group at the anomeric carbon replaced by alkoxy group. So this oxygen and this carbon, anomeric carbon, we call it as a glycosidic bond. And how do you name it? There would be ethyl. Since you have an ethyl group, ethyl, it's a beta facing up, beta D glucoside. It's not glucose anymore because there is a glycosidic bond. It would be named as glucoside. Ethyl beta D glucopyranoside. Okay, the proper name would be ethyl beta. Why ethyl? This group. Beta facing this group up. It's a D sugar. It's a glucose, D glucose. It's a pyranoside because 6-membered. and side because it's a glycosidic bond. So this is beta D-glucopyranose. This is ethyl beta D-glucopyranoside, which is an acetal. Okay. Now, if this is facing down, there would be ethyl alpha D-glucopyranoside, another acetal. Okay. And this is the mechanism for the glycoside formation. We have gone through this mechanism before when we were learning how to form the acetals, but let's look at it again. Now this oxygen hydroxyl group at the anomeric carbon grab a proton and form a protonated water molecule. And then we have oxygen next to this water molecule that forms a double bond and leaves the water molecule. So you will create this molecule with a positive charge on the oxygen. Now that we have created a good place for the alcohol to come and attack. So this alcohol can come either from the top or the bottom, the two sides. That's why we get axial and the equatorial glycosidic linkages. Okay, so this attacks and then the pi bond breaks and pi bond gives its electrons to the oxygen. So the two possibilities are this can come as equatorial position or it can also come as an axial alkoxy group. Once this is being formed, so when you add base goes and grab this hydrogen, base takes the hydrogen. So the glycoside, now it's been created. So this is a beta glycoside and this is a alpha glycoside. Alpha glycoside is going to be the major product, the one that is facing down. And then the reason for that this is, even though this is axial, that is more stable due to the fact that there is an effect called anomeric effect. Okay, so remember that this is your glycosidic linkage. So this is axial and then this one is your equatorial carbon. Okay, here you have oxygen and then here also you have oxygen. Oxygen has lone pairs, two lone pairs. So this is axial lone pair, this is equatorial lone pair. Now if the glycosidic bond is axial and you have oxygen carbon over here, and there is a possibility that this lone pair can overlap with the empty sigma star antibonding orbital on this place. So that overlap helps to spread out the electron density. Whereas here, when it is equatorial position, so that is not going to have that overlap. Okay. So the axial lone pair and the equatorial lone pair will not be able to overlap with this lone the empty orbital. And that is called the anomeric effect. Anomeric effect is a preference of certain substituents bonded to the anomeric carbon for the axial position. Like for alkoxy group, glycosidic linkage, when it is in the axial position, it's possible to do this overlap. So as a result, that's why it says alpha glycoside is the major product when it is like this. Okay. Just trying to see if I miss anything here when I'm explaining. No, that's all. Okay, good. Okay, so that is the oxygen glycosidic linkages, and similarly we can have a nitrogen glycosides as well. So this sugar reacting with aniline with the trace acid, so this OH can be replaced with the aniline group. Okay, that is a N-glycosides, N-phenyl alpha D ribosylamine, alpha N glycoside, or it could be N-phenyl beta D ribosylamine or beta N glycoside with the nitrogen. Just wanted to show you that. And we talk about the anomeric effect. Let's see. We'll stop here and then we can start again in the next session with the reducing and non-reducing sugars.